Hi, my name is Federico Toffano and I'm going to talk about some joint work with Nick Wilson and Paolo Viappiani for an efficient and exact computation of Setwise Minimax regret. Our work is based on multi-attribute utility theory, which is used to model user preferences for decision-making problems. The main characteristics of MAUT models are the following. First, we consider a finite set of alternatives A, where a decision maker has to pick his most preferred alternative. Second, each alternative is evaluated with a fixed number n of conflicting criteria. For example, the set A could be a list of apartments evaluated with three real numbers representing cost, size, and distance from the city center. Third point, MOD models suppose the existence of an ordinal value function, which is a function that defines the value of an alternative with a real number. In particular, an ordinal value function has the property that an alternative alpha is preferred to another alternative beta if and only if the value function of alpha is greater or equal than the value function of beta. With this presentation, we introduce a novel efficient algorithm to compute the Setwise Minimax regret in MAUT models. Roughly speaking, the Setwise Minimax regret measures the worst-case loss of recommending a set of alternatives in terms of utility units. The importance of this method has been highlighted by Viappiani and Boutillier in 2009, which have shown that it can be used to compute an optimal recommendation set and also a myopically optimal query set. Our algorithm applies to linear different preference model, where the user preferences are represented with a normalized weight vector of n weights. Roughly speaking, each weight wi defines the importance of the corresponding criteria evaluating an alternative. The value function corresponding to specific user preference w is given by the dot product between the weights vector w and the vector of a criteria evaluating an alternative alpha. Note that w is usually unknown, and thus we have a set of possible value functions, one for each point w in the user preference state space capital W. Val w instead is a function used to evaluate a subset B of alternatives, and it corresponds to the maximum utility value we can get from alternatives in B, supposing a user preferences W. For example, in this case we have a set of three alternatives evaluated with two criteria with a linear value function. The domain of the value function is expressed only with respect to W1, since the weights vector has to be normalized, and then W2 can be defined as 1 minus W1. To better understand the value function of a set of alternatives, in this figure I plotted the value function of the set beta gamma in red, which is defined as the maximum between the value function of beta and the value function of alpha. The setwise max regret of a set B with respect to another set A and a set of user preference W is defined as the maximum distance between the value function of A and the value function of B for any possible user preference. The setwise minimax regret of a set A for a given cardinality K instead is the minimum SMR of all the subset of A with cardinality K. Consider again the example shown in the figure. In this case, the red line represents the value function of the set B alpha gamma. As we can see, the setwise max regret of the set B alpha gamma is equal to 2 and it is maximized in W1 equal 1. In the picture, the setwise max regret in this case is highlighted with a red double arrow, and it is the distance between the green line 8,2 and the maximum between the black line 6,6 and the blue line 2,8. Intuitively, with a user preference corresponding to W1 equal 1 and thus W2 equals 0, the user cares only about the first criteria. Thus, in this case, recommending alternative gamma with the utility vector 6's, we would have a loss of 2 utility units since alternative beta has a score of 8 for the first criteria. Thus, a recommendation set given by alpha and gamma has a worst case loss of 2 utility units. So, if we consider the set B beta gamma instead, the setwise max regret is maximized in W1 equals 0. As we can see, also in this case, the SMR equals 2, since the distance with respect to alpha with blue utility 2,8 is 2 in W1 equals 0. Lastly, if we consider the set B alpha beta, we get a setwise max regret of 1 utility unit and it is maximized in W1 equals 0.5. The setwise regret of the set B alpha beta is also the minimum setwise regret of all the possible subsets of A with cardinality 2. Thus, the set B alpha beta minimizes the setwise minimax regret with cardinality 2 and it equals 1. The current state-of-the-art algorithm for the computation of the setwise minimax regret with a linear value function is a simple brute force method which computes the setwise max regret for each possible subset B of A with cardinality k. With our method, we keep track of the minimum setwise max regret R of the best subset B star found so far. Also, we consider only a discrete subset of user preference weight vectors. Then, our method is based on this fundamental property of setwise max regret. For any subset Bk with cardinality k of the input set of alternatives A, the setwise max regret of Bk is lower than the current upper bound only if for any user preference there exists an alternative with regret lower than the current upper bound. This property is important because we can test a subset Bk considering only a discrete subset of user preferences instead of the continuous preference state space capital W. Furthermore, thanks to this fundamental property, we can make use of a SAT solver to check if, given a subset C of A with cardinality less than k, there could exist a new set B star containing all the elements of C and improving the current upper bound. Since details of this method are a bit complex to explain, I'll try to give you an idea on how it works using the example that I've shown you before. Consider again the three alternatives alpha, beta and gamma with value functions shown in the figure. And suppose now a set of discrete user preferences W1 equals 0, W2 equals 0.5 and W3 equal to 1, and an upper bound R equal to 2. The idea is to create a SAT clause for each user preference in W prime. Each clause is defined by a set of Boolean variables x, one for each alternative with a regret lower than the current upper bound. So in this case, the clause corresponding to W prime is x alpha since the alternative alpha with blue value function 28 has regret 0 in W1 equals 0, and it is lower than the current upper bound R equal to 2. The clause corresponding to W1 equal to 0.5 is given by the OR of x alpha, x beta and x gamma, since each alternative has a regret lower than 2 in W1 equal to 0.5. In fact, alpha and beta have a regret of 1 and gamma has a regret of 0. Lastly, the clause corresponding to W1 equal 1 is x beta since the alternative beta is the only one with a regret lower than 2 in W1 equal 1. Also, we add to the SAT problem the constraint x alpha plus x beta plus x gamma equal 2, which is used to find a subset of cardinality 2. Now, if for example we want to evaluate if there exists a set with cardinality 2 containing gamma and improving the current upper bound, we also set to 1 the Boolean variable x gamma. But the SAT problem has no solution with this constraint. This means that none of the sets B alpha gamma and B beta gamma improve the current upper bound. In fact, the set with minimum setwise max regret is B alpha beta. In this slide, we show some experimental results. In particular, we show the average time to compute the setwise minimax regret with our method and with the current state-of-the-art procedure. We vary the size k from 2 to 3, as well as the number of criteria. The input set of alternatives has cardinality 50 and it is randomly generated. As we can see, with our algorithm we get a substantial improvement. Next steps could involve, for example, testing our method with a real dataset of alternatives in a preference elicitation process. Also exploring the feasibility of a constrained programming approach to further reduce the number of subsets to evaluate, and computing an initial upper bound with an heuristic to quickly discard sets with high max regret. Thanks for your attention. Any question?